All right, today we're diving into something really interesting, a brand new paper from Meta called Matrix. Now, this thing could be a game changer for one of the biggest problems in all of AI. What happens when we just run out of data? It promises some absolutely wild improvements in efficiency. But as we're about to see, those promises might come with a price tag so high that only the biggest players can afford to pay. Let's get into it.
So here's the situation. The entire AI world is basically speeding towards this giant wall. You see, to make these large language models smarter, they need to eat more and more data. But we're actually on track to run out of all the high-quality, human-written stuff on the internet in just a few years. It's a massive data bottleneck, and it's a huge problem for literally everyone in this space. So what do?
Well, one of the leading ideas is to just have AI make its own data. It's this concept called agentic synthetic data. The idea is pretty cool. You get a bunch of different AIs, think of them as agents like a writer, a critic, a fact-checker, and you have them all work together to create brand new information. But the problem is, the way we manage these teams of AIs today usually funnels everything through one central manager, and that just creates its own bottleneck. And that is exactly where Matrix's Matrix steps in. Instead of having that one boss in the middle, Matrix uses a totally decentralized peer-to-peer approach. So on the left, that's the old way, one central brain trying to direct all the traffic. It just gets overwhelmed and chokes. But on the right, that's Matrix. The agents just talk directly to each other. There's no middleman to slow everything down. It is a completely different way of thinking about the problem, and it's built to scale. The design is actually really elegant. The whole job, all the instructions, the data, everything, it gets wrapped up in this one single message. And that message just gets passed directly from one agent to the next, almost like a baton in a relay race. This completely gets rid of that single point of failure and, in theory, lets the whole system scale up to handle thousands, even tens of thousands of jobs at the same time. So what's the payoff for all this clever design? Well, according to the paper, Matrix delivers a 2 to 15 times increase in how fast it can generate data. And get this, using the exact same hardware as the old systems. I mean, that is a massive headline-grabbing number. Okay, whoa, hold on a second. 15 times faster? That sounds amazing. Almost a little too amazing. Performance claims like that are never quite that simple. We really need to dig into how they got that number and what identical hardware resources really means here. Come on, the numbers speak for themselves. Look at this. In one of their main experiments, the baseline system, the old way, was chugging along at about 2,600 tokens per second. Matrix, on that same test, hit over 41,000. That's a 15.4 times speed up. I mean, that is an objectively staggering improvement. Staggering, I'll give you that, but let's be crystal clear about the price you pay for that speed. To get that 15.4x number, they used a cluster of 13 H100 GPUs. They spun up 1,500 containers at the same time, and they were running 56 copies of a giant 120 billion parameter model. This isn't just identical hardware. This is a FANG-level supercomputer. I mean, who besides Meta or Google can actually run this stuff? Okay, you're right. That was their biggest experiment. But it's not some crazy outlier. Look at another one they did, the collaborative reasoner. Matrix still delivered a nearly 7-fold increase in throughput. A 6.8x speedup is still an absolute game changer. And the hardware for that one? Oh, just a cluster of 31 A100 nodes, which is, 248 GPUs. My point is exactly the same. These are beautiful results if you have a multi-million-dollar budget for a single experiment. For pretty much any university, any startup, any normal company, this is pure fantasy. It proves the concept, sure, but it doesn't prove it's practical for anyone else. But you're getting hung up on the hardware, and you're missing a really critical part of their claim. Right there in the abstract, the paper says Matrix gets this incredible speedup without compromising output quality. This means you're not just getting data faster, you're getting data that is just as good. There's no trade-off. You're not sacrificing quality for speed. Are you sure there's no trade-off? Because if you read deeper in the paper, they stop using that phrase, without compromising, and they switch to a new phrase, comparable output quality. Now that might sound like the same thing, but it's a subtle and, I think, a really important shift. If you're spending millions of dollars training a huge foundation model, is comparable really good enough for you? Or does that introduce just enough risk, just enough noise that you can't afford it? Let's just look at the actual quality numbers. For both of these experiments, the scores are, for all intents and purposes, identical. I mean, a difference in the third or fourth decimal place? That's just statistical noise. The data is clearly showing the quality is the same.
I just see numbers that are close, not identical. And when you are generating data at the scale of trillions of tokens to train a model, a tiny fraction of a percentage point difference in quality can actually multiply and compound into real problems down the line. That difference isn't zero, and at this scale, that's a risk.
Okay, let's get back to the core strength of this thing, scalability. This chart says it all. The red line at the bottom, that's the baseline system. As you throw more jobs at it, the performance just hits a wall and completely flatlines. Now look at the blue line up top. That's matrix. It just keeps going up, scaling almost perfectly. It doesn't choke. This is a picture of the bottleneck problem being solved right in front of our eyes.
It's a fantastic-looking chart, but is it really a fair fight? The paper says that the baseline system for this test runs on a single machine, a single node. Matrix, by its very nature, is a massive distributed system running across a whole cluster of machines. Of course, the distributed system is going to scale better. It feels like they're comparing apples to oranges. It's like they deliberately set up a baseline that was guaranteed to fail just to make Matrix look even better.
Fine. Let's talk about the distributed design itself. In solving that one bottleneck, the central manager, I think they might have just created a brand new one. I mean, think about it. When you have literally thousands of AI agents all talking directly to each other constantly, what do you think happens to the computer network?
Exactly. And you don't have to take my word for it. This graph is from their own paper, from their own monitoring tools. It shows the network traffic from all these agent-to-agent messages spiking to nearly 1 gigabyte per second. So they've just shifted the bottleneck from the central brain to the network cables themselves. You're just trading one problem for another.
But they knew that. I mean, this is a known issue in distributed computing, and they engineered a really smart solution for it called message offloading. So instead of trying to send huge chunks of data between agents, any big piece of content gets saved to a shared storage location. Then the agents just pass around these tiny, lightweight little pointers to that data. It is a clever solution, I'll give them that. But let's look at what it actually accomplishes. It results in a 20% reduction in that peak network traffic. That's good. But it only brings the load down from almost a gigabyte a second to 760 megabytes per second. That is still an enormous amount of traffic you have to deal with. It makes the bottleneck a little wider, but it doesn't get rid of it. You still need an incredibly high performance and very expensive network to handle it. Okay, let's try and pull this on together. I think we can both agree on this. Matrix is an undeniably brilliant piece of engineering. It's a system that was designed from the ground up to solve a very, very real problem at the absolute biggest scale of AI development.
I agree, it is technically elegant, but is it for everyone? The answer there is almost certainly no. It requires fantastically expensive hardware, it creates new problems you have to solve, like managing this massive network traffic, and, well, it seems perfectly designed for the exact problems and the exact resources of its creator, Meta. It's a tool for the hyperscalers, the tech giants.
And I think that's where we land. But there is one crucial takeaway here for everyone, no matter how big their computer is. And that's this core idea of row-level scheduling. This concept of processing every single little task on its own, the second a resource is free, instead of waiting to group things into big batches. This is all about making sure those incredibly expensive GPUs are never, ever sitting idle. And that is a powerful idea that anybody building big computer systems can learn from.
And that really leaves us with the big question, doesn't it? Is Matrix the blueprint that's going to solve the data crisis and lift the entire field of AI? Or is it more of a glimpse into a future where the price to play is so high that only the biggest tech giants in the world can afford to build the most powerful AI models? The answer to that is probably going to shape the next decade of this technology.